All right. So definite integrals. This all is based on the same concept we talked about on Monday about our goal is to find the area underneath a curve of some sort. Okay? So let's say we've got some f of x graphed here in the first quadrant. And I would like to find the area underneath it from A to B. Okay? So then the region would look something like this. So it'd be starting at that point on the curve, going to that point on the curve, so it would be all of this. Area right there. Okay? And what we talked about before was we went through and estimated areas like that by chopping that region into a bunch of rectangles, because both sides of that interval, if you take a look, they're nice and straight. It's just the top of it that's the problem, right? You've got this curve, and we have no geometry formula that we could necessarily use to figure out the area underneath that kind of a curve. So we just kept breaking it down into these smaller and smaller and smaller chunks. Well, if we take the number of those intervals and allow that to go to infinity, so we have an infinite number of intervals. Each one of those intervals is infinitely small. Okay, so we just keep going, and once we get to that point where we have an infinite number of them, then we have an integral. Okay, and the notation for that looks like this. It's kind of a stretched out S. It goes from A to B, and so here and here, so we put our limits. Okay, the limits are from where are you starting, what number are you starting at for x, to what number are you stopping at for x, of f of x, and then this dx. And that's called a differential. And we did look at differentials a little bit back in chapter 4, right? Okay, and we'll talk a little bit more down the road about what that differential really has to do with all of this stuff and why it's there. But for right now, just know notation-wise it needs to be there. Okay, we're not quite ready to jump into that yet, but we can start calculating some of these. So we're going to practice writing it the right way. In your calculations, that dx is not going to affect anything right now, though. It's just there in the notation. Okay, so let's just label up some of this stuff. So A is the lower limit. B is the upper limit. F of x is called the integrand. Which just means the function being integrated. And the dx is the differential. But for right now, it just shows the variable being used. That's really all it's good for at this point. Okay, so like I said, the concept is we've done this whole RAM stuff where we have these rectangles that we're adding together, and we've brought it to a point where it's going to be a limit as the number of intervals approaches infinity of that formula that we talked about before, where we do this LRAM, RRAM type of a thing. And then that ends up coming up with a formula for how we calculate one of these guys. Now, a lot of calculus teachers will go through and do all of that for you, show you how that all fits together, and it's great. But I think if you understand the concept of infinite number of rectangles, then we use this. For what we need to do, it's good enough. If you're really interested in why and how that all fits together, Your textbook does an excellent job of showing you that. If you want to read about it, talk to me about it later. We'll chat, whatever. It's fine. I don't want to take class time to do it. But pages 274 and 275, that's exactly what they're doing. They take 2 pages out of your textbook and just plow through all of that stuff. So I don't think we really need to worry about that. We're just going to use the notation correctly and start coming up with some actual calculations here. Okay? So what I'm going to do to start with is I'm going to just draw some pictures of some areas, and I want to see if you can write me an integral for that. Okay? Like, for example, if we have, this is f of x equals x squared, and let's say we want to go out to 5, and come up with this area here. So let's see, can you write an integral using this notation for the area that I just sketched in that picture there? So take a second, see if you can do that. Alright, so we should have something that looks like this. It's the integral from 0 to 5 of x squared dx. So, does that make sense? Just pulled the limits off of the picture. df of x is x squared. Got to have the dx. Done. Alright. What about... So I'll do this one. All right, so write me an integral for that one. And there's something going on different on this one that I want to talk about a little bit too. That's going to be important as we move forward. Bless you. Okay, so it should be the integral from pi over 2 to 2 pi of sine x dx. What's different about this picture from any other area one we've done so far?
It's got like an area above the curve.
It's got area above the curve and, well, okay, above the curve. Yeah, so there's area above the x-axis and there's area below the x-axis. Okay? And this can happen because functions do go below the x-axis from time to time. So, and we can still find that area as well. Okay? And so, when we calculate integrals, we're going to end up with what's called signed area. And this kind of goes against a little bit of geometry you guys have been taught. But in the applications we do with this stuff later on, it makes sense and it works. So, in this case, the area of this integral would be negative. This area above the x-axis is considered positive area, and this area underneath the x-axis is considered negative area. There's more negative area under here than there is positive area over there. So this overall integral that you guys have just set up is going to end up coming out to a negative number. Okay? So like I said, it's a little weird. You've been taught in the past that you can't have negative area. It doesn't make any sense. But when we start using integrals in context of some other things, the positive and the negative will start to have meaning. I can't jump to that right now to show you that, but it does. And you will see that later. But, okay, so doing some integrals. If the shape of the region that we're looking at is some kind of a basic shape from geometry, you guys can do these integrals already. Okay, and we're going to look at some of those to start with, and see if we can just come up with an answer. So rather than starting with the picture, I'm going to start with the integral. See if you can draw a picture, use the picture to tell me what the area is. Okay, and it should be some basic shape from geometry that you can do that. So let's do the integral of 0 to 3 of 2x dx. So like I said, draw yourself a picture, figure out where that area is, see if you can apply some formula from geometry that will work, and get the area. I'll give you guys a few minutes to do that. Alright, so did you guys all get the same thing as me? Okay, it makes a triangle, right? You've got this nice straight line, 2x. I'm going from 0 to 3, then I've created a triangle. 1/2 base times height. The base is 3. How did I know the height was 6? Yeah, exactly. Plug in the 3 into 2x, you get 6. There's the height. So 1/2 3 times 6, that's 9. So, okay. How about this one then? We'll go 2 to 4 of x plus 5 dx. I'll do this one with you. So, all right, so 2 to 4. We're still in the first quadrant here. So, and let's see, if it's x plus 5, that means it's going to have a y-intercept of 5, and then it's going to be having a slope of 1. It's another line. Looks kind of like that. And I want to go 2 to 4. What shape have I just made? Give you a hint. It's a quadrilateral with one pair of parallel sides. A trapezoid, exactly. What's the formula for the area of a trapezoid? Don't remember. Does have base in there. Base times. Yeah, there's two bases. Right, so base 1 plus base 2 times the height. But then there's also a 1/2 in there. So it's 1/2 base 1 plus base 2 times the height. Okay, now, base 1 plus base 2. You're used to seeing trapezoids that look like this, where you have a base and a base going this direction. However, trapezoids are allowed to look like that too. So just be careful. Your bases are the two left and right-hand sides. So what are the bases? 7 and 9. Good. You plug the 2 and the 4 into the function. So we've got 1/2 7 plus 9. What's the height of the trapezoid? 2. Yeah. So we end up with here 1/2 7 plus 9 times 2, which is just 7 plus 9. So 16. Okay, so triangle formula, gotta know it. Trapezoid formula, gotta know it. If you don't have it memorized, work on it. You've seen them before. Okay, oh, and one connection I probably should have done here. Because this came out to 9, you can write it like that. This integral equals 9, and the same thing with this one then. Since we got an answer of 16, that then equals 16. You're evaluating that integral by doing these little areas. Okay, got one more like this we're going to use some geometry with. And this one is going to look more difficult than it actually is. -3 to 3 of the square root of 9 minus x squared. And you might look at that and say, that's not anything we've looked at from geometry before. What the heck kind of shape is that? But you have. Consider this for a moment. It is y equals the square root of 9 minus x squared. I'm going to do a little manipulation on this formula and turn it into something that looks familiar to you. At least, I think. Square both sides first. Y squared equals 9 minus x squared. Add the x squared to the other side. X squared plus y squared equals 9. What's that the formula for? A circle. It's not an ellipse, it's a circle. As long as these two are not being multiplied by different numbers, it's a circle. So we've got a circle. What's the radius of that circle? 3. It's 3. Whatever this is, it's the square root of that is the radius. Which means whatever this is, the square root of that would be the radius. So we got a circle centered at the origin with a radius of 3. Now this square root though, it's not the plus or minus the square root, it's just the square root. Which means it's technically only half the circle. Which half of it is it? It's the top half. Yep. So we're looking at this area. So formula for the area of a circle is what? Pi r squared. Except we're only looking at half the circle. So pi r squared times a half. Or divided by 2. However you want to do it. Yeah. Okay. So radius is 3. So let's plug in a 3. So pi times 3 squared times a half. So that's going to get you, if we want to make it a fraction, it'd be 9 pi over 2. So this integral, the integral of the square root of 9 minus x squared, is 9 pi over 2. That's how much area we got there. Okay, so that's the idea as far as doing this with some positive area. When we come back tomorrow, we're going to look at some definite integrals where we have to play around with this idea of signed area a little bit. Okay, so again, we're going to be using formulas from geometry, but there are going to be some places where some things might cancel out because part of the area is positive, part of the area is negative. How do we deal with those? And then we will also look at a few properties of integrals as well, and that should be it. So, sorry I got to make you come back, but I do. So, is what. Okay, so we're going to start today by taking a look at just a few integral properties. Actually, in the next section, we're going to dig into some more involved properties of integrals, but today we're going to just hit a few that are going to be relevant to what we're working on in this section. As we talked about yesterday, this is an integral. All right, and that's read the integral from a to b of f of x dx. And then we started talking a little bit about this idea of signed area, that if the integral or if the function itself ends up going below the x-axis, we can have some area that's negative. If it's above the x-axis, that area is considered positive, and then sometimes there can be some cancellation that happens because of that. So if you have some area that is underneath the x-axis, then this is what we get. So the area then would be equal to negative a to b f of x dx when f of x is less than or equal to 0 as a result. Okay, so sometimes we want to find like the actual value of the integral using this signed area idea, and other times we just want to know what is the total area then. Okay, so this little property right here is if you're not talking about signed area anymore, if you just want to know physically how much area is there that you're dealing with. If it happens to be the function is underneath the x-axis, f of x is less than or equal to 0, then you just have to throw a negative in front. So what that ends up doing then is it cancels out the negative that you're going to get from the integral because that's signed area, and then it ends up being positive, and so you have your positive area again. So I'm just going to put underneath here, just to be clear, when not using signed area, then this is what you want to go with for those portions. So, give you an example. Let's say we've got f of x equals negative 2x plus 4. Let's say that's the function that we want to find the area underneath. And let's say we want to be on the interval 0 to 5. And I want to know what is the total area. So, i.e. not signed area. Okay? So then it becomes important to know where is this function above the x-axis and where is this function below the x-axis. Because if I just go ahead and find the area of the whole thing using the signed area idea, then I'm not going to be able to do it. Okay, so let's sketch a graph of this thing. Again, I've made one here where you guys can do it by hand. It's going to be, I think, a couple of triangles here. So we're going to go okay, so from 0 to 5, so this starts up at 4. And if I plug in a 5, I get, let's see, negative 10 plus 6, so, or negative 10 plus 4 is negative 6. It's going to end up at negative 6 when we're out at 5. It's going to go from here to here, so it's going to be something like this. Okay, and so that area we're looking for, it would be this triangle up here until it crosses the x-axis, and then we're looking at this area over here. Okay, so we need to know where this is. Otherwise, we have no idea how big these two triangles are, right? So, how do I figure out where that is? The function is negative 2x plus 4. How do I do what? Yeah, we're looking for a 0 essentially, right? So negative 2x plus 4 equal to 0. Alright, so negative 2x equals negative 4, so x needs to be 2. So we know this intercept happens at 2. Okay, so we can go ahead and just use our formulas from geometry to get the areas, but just to kind of drive home this point up here that we talked about, the area of this triangle then would be the integral from 0 to 2 of negative 2x plus 4 dx. And this area down here would be the integral from 2 to 5, except negative, because we're not looking for signed area anymore, negative 2x plus 4 dx. Okay, so that's where that little rule is coming into play down there. We've got a portion of this thing that's underneath the x-axis, so in that portion, if we're looking for total area, we've got to flip the sign on that and make it positive. Now, doing the calculation using the geometry formulas, you don't really need to concern yourself with that too much, because you can just plug numbers in and find it. So let's see, this triangle right here, what would be the area then? You've got both dimensions that you need there. Four. Yep, 1/2 base times height. Base is 2, height's 4. So that should be a total area of 4. And then this triangle over here, we've got a base of 3 and a height of 6. So what would be that area then? 9. All right, so the total area involved in this would be what then? 13. Yeah. Now let's just say for the sake of argument, because we've got it right in front of us, I was going to do signed area on this one. What would the answer be then? So I've got 4, an area of 4 above, and I got an area of 9 below. So if it's all signed area, what's the total? Negative 5. Yep. When we get into applications, depending on what we're doing, we might want one or the other of those. We'll be using both and for different things. Okay? So that's the difference. So, okay. And then there's this other property, and we actually just used it to come up with this. It's a pretty intuitive idea, but I might as well write down the property here. The integral from a to b of f of x dx equals the area above the x-axis minus the area below. And this is when you are using signed area. Okay, and like I said, you guys knew to do that without me really having to tell you that, just based on how like the geometry of it gets set up there. But that's the idea. For an integral in general, when using signed area, it's the area above minus the area below. Okay, and sometimes that result comes out positive, sometimes it comes out negative. It just kind of depends on what you got. Okay, if there's more area above or more area below. So, okay, so we're going to use this idea of signed area to do a little exploration. So if you guys would turn to page 279 in your textbooks, we're going to take a look. I'll give you guys a little bit of time to work on this one, but should be looking at this. All right. So I'm going to read this to you real quick so you can kind of hear it and see it. It is a fact, which we will revisit, and we will, that the integral from 0 to pi of sine x dx equals 2. With that information, what do you know about integrals and areas? With that information, what you know about integrals and areas, what you know about graphing curves, and sometimes a bit of intuition, determine the values of the following integrals. Give as convincing an argument as you can for each value based on the graph of the function. Now, I'm not going to make you guys write out arguments for them, but we will discuss them in a little bit. Okay? So what I'd like you to do is, with your table partner, whoever you have with you there, see if you guys can work together and come up with as many answers for these as you can. Okay? And then don't do number 10, just do 1 through 9. That's it. Yeah. Do what? Oh, you guys got to go do that. Yeah, you can go do that now. It's fine. All right. I'll give you like maybe 10 minutes, 15 minutes. I don't know. We'll see how it goes. But go ahead and give these guys a try. Take a look at the graph next to it, too. That's there to help you. Okay? That's the area that is 2. So use that fact. See if you can come up with the rest of them. All right. So we're going to finish up here by looking at discontinuous integrable, that's how you say that, integrable functions. All right, so I'll give you an example of a function that is discontinuous, yet you can take an integral of it. So if we had -1 to 2, the absolute value of x divided by x. Now what I'd like you to do, because I'm guessing you guys probably don't have a picture of this function in your head, take your calculator out for a second and graph this thing. Absolute value of x divided by x, and see why this function is discontinuous. So what does this thing look like? Looks like a couple of lines. A couple of horizontal lines, right? Something sort of like that. What kind of discontinuity are we looking at here? It's a jump discontinuity, and where does it happen? When x is what? 0. Okay. So it's definitely discontinuous. Thing, I can still find the area under this from wherever to wherever, right? The fact that there's a jump discontinuity does not affect my ability to integrate this thing, to find the area, signed or otherwise, on it. So now, if you're given an integral And they don't tell you whether we're talking about signed area or total area. Assume it's signed area then. Okay? So we want the integral from -1 to 2 of this. Okay? Well, based on the graph, it's at -1 and then it jumps up to 1. Okay? So I kind of have two portions here. Maybe I should just draw this graph on here too, just so we can talk about it a little bit easier. So from -1 out to 2, so we've got this rectangle, and then we've got this rectangle. How much area is here? Remember, this is at 1 and this is at -1. So how much area do I have in this one? 1. And how much area do I have up here? 2. So I said assume signed area if not otherwise told. So this is signed area then. So what's my answer? 1. Yep. Okay. 2 minus 1. 1 for that. Okay. So a jump discontinuity, not a big deal. Okay. There are other ones. If you have a removable discontinuity, not a big deal. That one works too. So here's an example of that. Let's say we wanted to do the integral from 0 to 3 of x squared minus 4 over x minus 2. Okay, so in that one, can you guys look at that function and tell me where the discontinuity is going to happen? At 2, right? Which happens to be in the interval. Now here's an aside. What if I had a spot in my integral where there was like an asymptote or something like that, but it wasn't in the interval that I was doing the integral for? Would it matter? No. Because I'd only be taking a portion of that function to go get my area, right? And if that asymptote that might be creating that problem is not in that portion of it that I'm taking the integral of, it doesn't matter. Like, okay, it can do whatever it wants over here. I'm only concerned with this little chunk of it over here. I'm going to find that area. Now this one looks like it might create a problem because the 2, the bad spot, is inside of this interval, though, from 0 to 3. So if it happens to be an asymptote, asymptotes are bad. Because if you try to find the area as you come up to an asymptote, what's going to happen to that area? It's going to keep going to infinity, and you're not going to be able to actually get a finite number for that. So you can't do anything with asymptotes. But this doesn't have an asymptote. Why doesn't this thing have an asymptote?
It has x minus 2.
Right. You can remove it, right? It's a removable discontinuity. It's not actually an infinite discontinuity. So this is the same thing as going 0 to 3 of x minus 2, x plus 2 over x minus 2. In which case we have the same thing as the integral from 0 to 3 of just x plus 2 dx. Okay, so let's draw a picture of that. X plus 2, we can do that. Let's see, from 0 to 3. All right, so we're going to start at 2, and we're going to end up at 3 plus 2. We're going to end up at 5. So we're going to go here to here. So we're really looking for this area in here. Okay, now at 2 though, I said there is a removable discontinuity. So technically, there's an open circle right there at 2. Okay, but that hole is infinitely small. Okay, so because of that, when we're looking for the area underneath this curve, even though it's undefined right here, the two areas on either side of it are infinitely close to one another, so it's as if they're not even there. So it doesn't even affect the area. So you can still just think about it as one big trapezoid, and it's fine. It works. Okay, so what is the area of that particular trapezoid? Or at least maybe give me my dimensions here. What's the height of it? Height is 3, yep. And what are the two bases? 2 and 5, yep. Good. So it's going to be 1/2 times 3 times 7. So half of 21 is 10.5. So we can still do that. So I guess moral of the story here is, if it's a jump discontinuity or a removable discontinuity, integration can still happen. If it's an infinite discontinuity, then we got problems. Can't do that. Okay? We will actually talk more about those in Chapter 8. In Chapter 8, we're going to come back to integrals where there's asymptotes. And actually, we will be able to calculate those then. But that's not till like the last chapter of the entire year. So, anywho. So, any questions about any of this stuff so far? All right, very last thing I want to show you, just in case you didn't catch it last year in pre-calc, doing an integral on your calculator. Okay, just so we have this skill moving forward. Wanted to show it to you today while we got a little bit of time. You guys remember when we did derivatives on your calculator? Go to math, and then it's at the end of the menu there, that n deriv. Well, one below it, fn int, that's your integral. So if you grab that one, unlike the derivative only requires 3 inputs. The integral requires 4. And here are the 4 things that it needs. The function that you're going to use, so what's the f of x in the integral, the variable you're using, and then the upper limit and the lower limit. Okay? Actually, it goes the other way. Lower limit, then upper limit. So it goes in that order. So function, x, lower limit, upper limit. So let's say, like this last one that I just did, I want to do the integral of x plus 2. Okay? So I'm going to go x plus 2, comma, x. And we went from 0 to 3. 0, comma, 3. And we should be getting 10.5 here. Yep. Now, does anybody have the fancy-dancy calculators where it actually makes an integral for you? Okay, you know where to put everything? It's pretty intuitive at that point. It looks just like the other way we were writing them. Okay. So that's the idea. So I'm going to write that down just for those of you that don't have the fancy ones that set it up for you. So when you're doing fn int on your calculator, you need to have the function, x, a, and then b.
Does that give you absolute area or sinusoidal?
That always gives you signed area. Yep. Whenever you do an integral, it's signed area. So if you don't want signed area, that's when you have to start manipulating the integral to get it to be what you want, which we'll do more of that later. But yeah. So, all right. I'm going to let you guys get to work on some stuff here then. Got a decent chunk of time yet today.